Hey everyone. So today we're going to be doing a quick video showing you how we investigate interactions using R, specifically interactions that we find in a linear model. Remember, we can use linear models with multiple predictors to do a few different things. One of those might be to improve your predictions. Another reason might be to control for things. We saw that in the previous video. And finally, there's interaction effects that we may want to investigate. So let's get right into R and see how we do this. Okay, so I've put myself up here in the top corner so we can see some plots that I might make below us here. So the first thing we're going to do is load up a few packages that we're going to be using for this session. So the first one will be flexplot. So we use the function library flexplot and load that. So I'm just using Control-Enter to run those. You can see that command loaded. We're going to be using the EM_means or estimated marginal means package. We may be using the tidyverse package. It's always nice to have loaded up in case you need to filter your data or something really quickly. And finally, we're going to be using the CAR package or companion to applied regression. Now, if you don't have some of these packages installed, just make sure to install them and then load them up using the library function. Okay, so the first thing we're going to do is look at an interaction example where we've got one categorical predictor and one numeric predictor. Specifically, what we're asking here is, does the relationship between the number of people at a party and enjoyment of that party depend on personality type? So personality type here is our categorical variable, and the number of people at the party is our numeric predictor. Enjoyment is therefore our outcome variable. So what we're going to do is first load up the party people data set. So you can find that linked below. And I'm just going to put that into an object I'm going to call party people. So I've loaded that up and we can see it in the environment right behind me here. Now, one of the first things that I think I've taught you to do is just have a quick look at your univariate plots just to see if there's any problems that are obvious in your data. So the first thing we're going to do is look at our outcome variable and see if there's any problems. So we're going to use the flexplot package and we're going to say enjoyment tilde or as a function of 1, which basically says create me a histogram of enjoyment. Now we see there's a reasonably symmetric distribution of the data, so it looks fine. There's no massive outliers or anything. The next one we'll look at is the number of people, and we'll see if there's any problem with that. And again, the histogram, it looks like it's a tiny bit skewed, but it seems fine. We're going to look at type, which is basically whether you're extrovert or introvert, and this will give us basically just the number of people in each group. So if I run that, we see, in fact, it looks like they're both reasonably similar in terms of size. And then finally, what I'm going to graph here is enjoyment as a function of number of people. And I'm going to put that in different panels for the type of person you are, whether you're an extrovert or introvert. So that's what this structure is saying. Enjoyment as a function of number of people, paneled on type. And again, we've got data equals party people, and I'm just going to draw a linear model or LM through that as well. So the method we'll use is LM instead of letting it do a lowest line. So when I run that, what we see is we get our graph down below us that shows us an interaction. Now, an interaction just basically says the effect of one variable on our outcome depends on the third variable. And here, what we're talking about is the effect of the number of people at the party and the enjoyment of the party depends on whether you're an extrovert or an introvert. So here we see that if you're an extrovert, increasing number of people at the party increases your enjoyment. That's that positive slope. Whereas if you are an introvert, it looks like increasing the number of people at the party decreases your enjoyment. So this is what we mean when we say we've got an interaction. That means we can't really say that enjoyment does anything. Does it increase? Does it decrease as the number? Well, it depends on what type of person you are, an introvert or an extrovert. So once we see that, we can actually create a model of that using LM. So the way we do that is exactly the same ways we've done it in previous videos. So I'm going to call this object M. So it's a new model I'm going to call M. I'm going to use the LM function for linear model. And it's going to be basically the same as this. It is enjoyment as a function of the number plus type plus, this is an interaction term, the number by type. So when I create that model, we see we get a standard linear model. And if I do an ANOVA of that model, what we see is the overall effect here is that we've got no effect of number, which is interesting. You think, well, wait a second. This would tell me that number has no effect. But the thing is that in the presence of an interaction, these main effects, number and type, they can't be interpreted on their own. You have to either only interpret the interaction effect or at least interpret these in the context of the interaction effect. So we see that we've got a number by type interaction where we've got a large F ratio and a really small p-value. So we may want to then look at the coefficients of the model. Now, before I do that, I just want to show you that we can actually specify this interaction model in a different way. That's sort of shorthand. If we look at M here, I've got M, LM, and it's enjoyment as a function of number asterisk type. So you can see all that's doing is it's combining these two terms. It's plus type plus number multiplied, or the product between number and type. And this is just a shorthand version of this if you're going to be creating an interaction between those terms. So if I do that, what you can see is I'm going to create that model. I just overwrote the model, but if I run the ANOVA of that, we see that the values we get out are the exact same thing. It's the exact same thing to do this. It just means that if you want to do something separate with the interaction term, you can by writing it out this way. So just a quick note that these are basically two ways to write out the same formula. Okay, so now that we've created that model, we may want to visualize that and see if there's any diagnostics or any problems that we may need to attend to before we start to interpret what all these things mean. So I'm going to zoom this out so we can see it a little bit better. So what we see is it's created our model where we've got a positive slope for extroverts and this negative slope for introverts, just like we saw when we just plain graphed it. Our histogram of residuals, we look at this, we see it looks like pretty symmetric, pretty normal distribution. So it doesn't look like we've got any problems with non-normality, any real problems. It looks like our residual dependence plot has a pretty flat line through it. So it doesn't look like there's a real curvilinearity left in this data set. And our spread location plot is pretty flat here, which suggests that the variance at all these different levels of the fitted variable are reasonably similar. So we don't have any problem with heteroskedasticity. So we can be pretty confident that we're okay with proceeding with interpreting this model. So what we're going to do is look at a summary of the model. So I'm going to use the summary command and see what the coefficients are that we get out of this model. So what we see is when I run this, we get our intercept and we get coefficients for number, coefficients for type introvert, and a coefficient for number by type introvert. So because we see it's type introvert, we know that what the model has done is used the extrovert as the reference group here. So what this will say is that enjoyment for extroverts when the number of people at the party is 0 is 4.78. 8. And the next coefficient suggests that 024 here, that is the slope for the extrovert group here, which basically says that for each increase in number of people at the party, for each extra person at the party, enjoyment will increase by 0.024 points, whatever that means. So the third coefficient, type introvert, basically says it's 0.317, and that's the difference between the intercepts for introvert and extrovert. So basically you could just take 4.78 and say, oh, the intercept for introverts will be 4.78 plus 0.31. So about 5.1-ish. And then finally, the last slope, negative 0.046, is the difference in the slopes between extroverts and introverts. So because we know that the slope for the extroverts is positive 0.24, and the difference between the slopes is negative 0.045, that means the slope for the introverts must be negative about negative 0.02-ish, maybe 0.021. All right, so basically that's how we can interpret these. But it's a little bit cumbersome maybe to do all of this math, so we can actually use some functions to get those values out for us. So one of those functions we can use is actually called the emtrends function. So emtrends comes from the emmeans package, and basically the emtrends will give you individual slope values. So the slope for the extrovert, which we already know was 0.024, and it will tell us what the slope for the introverts, which we tried to calculate out by using these numbers, but this one will give us it directly. So what we do is we specify emtrends, we use m, that's our model, pairwise as a function of type. So what we're doing is we're going to say we want to compare as a function of whether you're an extrovert or an introvert. The last thing you need that's different in comparison to the emmeans function is this var function. This basically says, well, what variable do you want to have on the x-axis that we're going to be looking at? And this one in this case is number. So we've got pairwise as a function of type, var equals number. So if we run that, the output that we get down here shows us our two slopes. So 0.024 for the extroverts, and our introverts was, like we calculated, negative 0.021. And we get some standard error, degrees of freedom, upper and lower confidence limits for those slopes. But also what it does is it gives us a contrast, or basically compares those slopes to say, are these significantly different from one another? Now, it tells us what that difference is, 0.046, which is actually what we saw up in the summary, as well as a t-ratio and a p-value for that to say, basically, is the difference between these slopes equal to 0, and what's the probability of seeing that value if it was equal to 0? Now, another way we can get at this information is by using the simple slopes, or sim_slopes function, which is included in the interactions package. Now, if you don't have that package already installed, you can go ahead and install it. I've already got it, so I'm just going to load it up using the library function. So once you've got it installed, make sure you load it up using the library function, interactions. Now, what we're going to do is we're going to use the simple slopes function, and what this is going to do is allow us to look at the individual slopes and test them each against 0. So before we are comparing them against each other, this is going to compare them each against 0. So what we do is we use sim slopes, we specify the model, we have to tell it the predictor is number, so that is the predictor, which is our x value. And then mod x basically says What is the interacting factor on X? What's modifying X? And then we specify the data type. So when we do that, we run SimSlopes. What it does is it gives us a simple slopes analysis, which tells us what the estimated slope is. So for the extroverts, our simple slope says our slope is positive 0.2, and for introverts, our slope is negative 0.2. So this is just rounded up and down slightly. It gives us standard errors, t-ratios, and a p-value of whether or not that value is different than 0. That slope is different than 0. Okay, finally, one thing you may want to do is determine whether or not there are differences between extroverts and introverts at various levels of number. So, are there differences in enjoyment between extroverts and introverts when there's very few people at a party, 0? Or is there a difference between the extroverts and introverts in enjoyment when there is a lot of people at the party, like 90? So we can actually use the EM means, or estimated marginal means function, to take a look at this. We just need to give it an extra term for the type of data that we're using here, which is a numeric predictor. So we use EM means, we specify the model M, we tell it pairwise as a function of type by number. So this is saying, give me a pairwise of the interaction. And then what we need to do, because this second one is a numeric variable, we have to tell it what values do we want to compare at. So we say, we want to compare at 0, 30, 60, and 90. But you can make these values whatever you want. But you need to combine them into a list in this way. So we concatenate this with C, 0, 30, 60, 90. And we have to say a number is equal to that, and we create a list out of that. So it's a little bit complex of a structure, but it's just list, number, concatenate, levels. If you use this structure, you could just input whatever numbers you want in here. Now, when I run that command, what we see is we get this entire list of different values. So we have, in this case, we've got our means, so extrovert at number 0 and introvert at number 0. What is the mean? 4.78 and 5.10. So that is actually the intercept. In fact, if you remember from the summary function, we were actually able to calculate that out directly. Then we see that for extroverts at 30 people, the value would be 5.51. So that would roughly correspond to here. And for introverts, 4.45. And that would roughly correspond to this point on that red line as well. And so on and so forth for the 60 and 90s. Now, because we've specified pairwise here, it does all of those comparisons for us and says, okay, well, is extrovert at 0 different than introvert at 0? And it gives us an estimate of the difference and a p-value. So this one says the p-value is 0.9, so there's no difference between them. And you can see all of these different comparisons. And it turns out that some of them we may not be that interested in, and other ones we might be interested in. The ones we can see really right off the bat that are not significant are extrovert versus introvert at 0, and then extrovert versus introvert, but extrovert at 0 versus introvert at 30, and this one here, which is introverts at 0 and extroverts at 30. So there's a few, no, it doesn't look like there's any others that are actually not significant. The rest of those differences are significant. All right, so let's move on to our second example, which involves using two categorical predictors. And here we're going to ask the question of whether the effect of diet type on weight loss depends on gender. So diet type and gender are our two categorical predictor variables, and weight loss is our numeric outcome variable. So what we want to do first is read in our diet data set. It's linked below. I'm just going to read it in to an object called diet. And this time I'm going to also specify strings as factors equals true, because I want to make sure that the different types of diets and things like that are categorized as factors. So I'm going to read that in. Now, again, we may want to look at the univariate distributions of things to make sure there's nothing too badly outlying. So we see weight loss looks like it's reasonably normally distributed. We've got 3 different diet types, A, B, and C, and we see that there's a reasonably similar number of people that have done each of these diet types. And then we've got our genders. It looks like we've got a few more females than males, but otherwise it looks pretty good. It's not too unbalanced. Now, we can look at this, the interaction between these factors in 2 different ways. So the first way we'll look at it is weight loss as a function of diet type plus gender. So what this is going to do is basically put both of the lines on the same plot. When we see that, we see basically we've got the red dots here. The red markers are for females, and the greenish blue dots or markers here are for the males. So we can see the difference between this all sort of plotted on one. Diet type along the x-axis and then weight loss on the y-axis. Okay, so we could also plot it if we wanted the same way, weight loss as a function of diet type, but we could instead panel on gender. So this would just give us 2 separate panels. So it depends how you like to visualize these things, but in this case, we've essentially done it in panels. I'll leave it up as the previous figure that we've just seen before here while we go through the process. So again, what we're going to do is we're going to create a model of this by putting in weight loss as our outcome variable, and then diet type by gender as our interacting factors here. Data equals diet. Now when I run that, I get a new model. I've called it M again, so it just overwrote my old one. It just makes my life easy just so I can say M all the time instead of making typing mistakes and things like that. So we may want to go ahead and visualize that. So if I visualize that, I'm going to pop this out and we're going to just look at the diagnostics real quick. So again, we've got the same sort of plot here that we saw before, where it's just plotted on 2 panels. Our histogram of residuals looks reasonably good. It's a little sort of platykurtic actually. So it looks like there's sort of these long tails. There's the fat tails out here. So that might be a concern, but not at this point, not really. And also our spread location plot looks like it's a reasonably flat line. So most of this I'm not too worried about. So we'll just go ahead with this analysis. So the next thing we might want to do is do an ANOVA to see what the main effects or the interaction effect more specifically tells us. So here what we see is we have an interaction of between diet type and gender, where our F value is 3.15. So the p-value is significant, but it's only 0.048. So it's close, but it's still saying that that's a significant interaction. And remember, we can't really look at the main effects in isolation, so they might be a little bit meaningless in this case when you've got an interaction. So we may want to then look at the summary so we can see what the coefficients are. Now, the coefficients in this are going to tell us essentially how we get to the different means. So the intercept here is going to be for one of the groups, and because we know that it's telling us male is the other group, it means it's the intercept for female. And the intercept for female for which diet type? Well, we know we've got type B and C here, so it must be the value for female diet A. And we see that is negative 3.05. Type B here, that's just the slope or the difference between means between female type A and B, and this is the difference between means for female type A and C. We can also calculate out all of these different values for the male. So essentially, we could see that the intercept here, the two intercept differences would be negative 0.6, and we can go through the process of calculating all of these different values, but it's a lot easier to actually use the estimated marginal means function to get that out for us. So this is a lot easier than in the previous example because all we need to do is tell the model that we want. So estimated marginal means, EM means, of M, and then it's pairwise as a function of diet type by gender. If we do it this way, what this is going to do is provide us with all possible pairwise comparisons. So female A and B and female A and C, etc., and even female A versus male C, which we might not be that interested in. But this will give us all of the different comparisons. So if I run that, it will tell us not only the different means, like I said, we could calculate directly from our beta coefficients, but this way it gives them to us really easily in a really clear table. So we've got our estimated marginal means for each diet type and each gender. We've got standard error of the mean for each of those and upper and lower confidence limits. Then we also get all of the different contrasts, so all the different comparisons. So that would be diet A for females versus diet B for females. Is that different? And it says the p-value is 0.99. No, it is not. We also have diet A for females versus diet C for females, and we see that one is significantly different. So we could go through this list, and in fact, it's easier in this case to see which ones are significant. So there's this one. If I look down the list, there's this one here. So B for females versus C for females. And then pretty much that's it. So it looks like the only differences in here are that diet C is different in females compared to diet A and B. There are no other significant differences in this whole data set. Now, it may be that we were only interested in diet types within each gender. You didn't want to look at the differences between diet A in females and diet A in males. That might not be something that you're interested in. So if we use this structure where we say we're going to look pairwise of diet type, and this is paneled on or basically separated by gender. Now, when I run that, what we see is we will get the estimated marginal means separated by gender, but this is still the same thing we're going as we saw earlier. But then the contrasts that we get are only between diets A and B and A and C and B and C within females, so we can see those differences, and the differences between diets within males. So that's another way you may want to go about looking at the differences between these diets or the interaction effect and trying to break that down to see where the real differences truly lie. Okay, finally, we're going to look at another last example. That will be with a numeric outcome and two numeric predictors. So we're going to use a data set that's actually included within the FlexPlot package called relationship_satisfaction. So you don't have to worry about loading up this data set as long as you've got the FlexPlot package loaded. Remember that we typically want to look at the univariate distributions to see if there's any problems with our data. I'm not going to bother doing that. I've just shown it to you in the last two. I know there's no real problems with this data set. So we're going to go straight into visualizing our interaction effect. And just like we did last time, we could visualize this in two different ways. So we're interested in relationship satisfaction as a function of conscientiousness and interests. So we're going to look at how those two things interact. So if I run this command and we're using data equals relationship_satisfaction and method equals LM so that it draws a linear model through those. Now, if I run that command, what we see is we get a plot down here that has 3 different lines. So we've got conscientiousness on the x-axis and satisfaction on the y. So we're saying, how does satisfaction change with conscientiousness? And how is that different, or is that different when you've got different levels of interests? Now, in order to plot 2 numeric variables, one of them you really have to sort of pseudo-categorize. And in this case, what we've done is we've categorized interests into low, medium, or high. So do you have similar interests? Low values would be not very similar. Medium would be medium similar interests, and high similarity in interests. So another way we can do that is, instead of having them basically grouped and put 3 different lines, we could actually put them in 3 different panels by using this type of structure here. So conscientiousness paneled on interests. So if I run that, we see basically the same thing, and it gives us maybe an easier way to look at it in this context. So what we see is that when interests are low, it looks like higher conscientiousness actually leads to lower satisfaction. But when interests are medium or interests are high, higher conscientiousness leads to at least slightly greater relationship satisfaction. So we can create a model out of this again by using the exact same structure. So remember, LM doesn't really care whether or not these variables are numeric or whether they're categorical. We can put them in, and then we just have to interpret them appropriately. So it's exactly the same structure as we use for the flexplot function. So it's satisfaction tilde, or as a function of conscientiousness by interests, or star interests. Data equals relationship satisfaction. Now I'm going to run that command, and I get my new model that just overwrote my old one that I had called M previously. We're going to use the visualize function out of the flexplot package to have a look at any diagnostic plots we want to see. So I'll zoom this out for us, move it over here. And again, looking at the histogram of residuals looks fine. The residual dependence plot looks like it's got this big curve right at the top. That may or may not be real, because it looks like it's really being driven by 4 data points here. So that might be something we'd want to maybe consider trying to fix in a different analysis, and we can see how we do that in future videos. And then the SL plot looks like it's got a small increase in variance as the fitted value goes up, but it doesn't look like it's big enough for us to worry about a problem with heteroscedasticity. So I wouldn't be too worried about this at this point. So we'll just get rid of that. Now, again, once we've made this model, we can use the ANOVA function to look at the different components of the model. And here we're interested in the interaction effect. So there is a significant interaction effect with an F ratio of 19.07 and a p-value of 1.7 times 10 to the negative 5. So that's great. We can then look at the summary to determine what those beta coefficients are telling us. So if I run a summary, we get these 3 beta coefficients. Now, the intercept basically says, what is our value for satisfaction when both conscientiousness and interests equals 0? And what that says is that our intercept is 43. So our estimate of satisfaction would be 43. And as conscientiousness increases by 1 point, we have a decrease in satisfaction of 0.0246. Furthermore, as interests increase by 1, we have an increase in relationship satisfaction of 0.034. Now, finally, we've got an interaction effect here. So that is the significant interaction effect. We probably don't care too much about these. We can't really interpret them on their own. So we've got this interaction effect of 0.0102. Now I've put up here what this interaction term means here is that the effect of conscientiousness on satisfaction changes. And we can see that in these graphs. So it changes in a positive direction by 0.01 for each unit increase in interests. So as interests increase, we see that slope changes positively. It goes more and more positive as we go in higher and higher interests. And that is what it says. So this slope is changing in this way as interest goes up by 1. Now, in order to break this down a little bit further, we can again use that simple slopes function to say, are these slopes different at different levels of interest? So is the slope when interests are low or at the mean level or at high levels any different? So again, we specify this by saying we want to do a simple slopes of the model, and our predictor is conscientiousness, and our modifier of x, or our interacting factor, is interests. So when I run that, what we get is a different slopes analysis that gives us the slope of conscientiousness at 3 different levels. So at -1 standard deviation from mean interests, when interest equals 20, and then when the mean of interest level, when interest equals 40, and a higher level, that's 1 standard deviation, when interest equals 60. And what we see is that when interests are low at -1 standard deviation from the mean, our estimated slope is -0.3, and that's not significantly different from 0. It looks like it's pretty flat, basically no effect. Whereas when interests are sort of medium or interests are high, it looks like our slopes are significantly different. So the slope is 0.17 at the mean level of interest, and our slope for conscientiousness is even greater, 0.37, when, and that's significant when interests are relatively high. All right, so hopefully that gives you an introduction on how we go about running these different models to look at interaction effects in R, whether you've got 2 categorical predictors, a categorical and a numeric predictor, or 2 numeric predictors. All right, so we'll see you in the next video.